Hi. So in this recitation section, we are going to see how to use strong induction to prove a statement. So for that, I pick two specific examples here. This is the first one, and this is the first one, and then the second example. And then when we solve these two examples at the end, I'm going to give you some hints about how to proceed on your homework, because I realize that a lot of you are going to be lost on some part of that. So let's just jump into that and try to show the first expression. So we can start with the second one. I'm going to start with the second expression. So our goal is to show that if you have u1, if you have u1 equal to 2, then u2 equal to 6, then we give this definition, request definition un equal to n minus 1 plus 2n. The goal is to show that un equal to n times n plus 1, right? So for n greater or equal to 2, so that's what we have to show. Let me call this property Pn. This is our property Pn that we are trying to show. And the principle of mathematical induction say that the mathematical induction principle say that if you want to show something that the property Pn, if you want to show that the property Pn, what you do on the base case, the base, you show P of n0. So n0 is the smallest value of n. So in this case, n had to be greater n had to be greater or equal to n0. That's what we mean, right? Now then you assume the inductive hypothesis, inductive step, which include inductive hypothesis. For the hypothesis, you assume that P of n is true. Then you want to show that P of n plus 1 is true. So that's the inductive principle of mathematical induction. Now for the strong induction, so for the strong induction, most of the time, or especially when you have to deal with a recurrent relationship like what we have here, just like a recurrent relationship, that means you can get the next term based on what we have for the previous term. So what we do is generally for the base case, you can have more than one thing to check. So for the base case, for the base in the strong induction, you can check P of n0, you check P of n1, you check P of n2, right? Depending on how many base case you have. Let's say in this case, in this particular example, this example that I have here, we have two base case. So basically for this, we have n0 is going to be equal to 1, and then we are going to have n0 is going to be equal to 2, right? Because we have these two base case. We don't need this in this case. So when we solve that, we are going to see what I mean by that. And then for the inductive step, what you do is you assume that for a certain integer m, let's say we have m, an integer which is greater than everything behind. So this is greater than, yeah, let's just say for a certain integer n. So what we have such that n had to be greater than, n had to be let's call m, so that m had to be greater than some numbers behind, right? Than some number that we have behind there. So the way that we represent that is, so we need to have P of n0 and P of n1 and P of n2 up to and P of m, right? That's my m that I said over there. So I need this to be true, all this to be true individually. So P of n0 had to be true, P of n1 had to be true, and so on up to p of n, p of m. Then we need to show that p of m plus 1 is also true, right? So basically we assume that these statements are true up to a certain m. And how about if you move on the next step? Is that going to be true or false? So that's what we call the principle of mathematical induction. So basically we assume all this to be true. Because these are true, we can just assume that this is going to be this is true. Then we go from here, then we prove this, right? Then now let us just use that to prove our statement. So again, the statement was un equal to n times n plus 1. So we need to show that, and they gave us u1. This was given u1 equal to 2. We give u2 equal to 6. Then we give un equal to un minus 1 plus 2n, right? So for the base case, because this is my property Pn, right? So this is my Pn. So for the base case, I'm going to check P of n0. So and also I'm going to check P of n1, right? So for this one, n0 equal to 1, right? So this is 1. So what is u1 equal to what? Because this is the property that I'm trying to prove, I'm going to use that u1 equal to 1 times 1 plus 1. Just give me 2 times 1. This is going to give me 2, which indeed equal to this. So therefore P of n0 is true. How about n1? So n1 equal to 2. So this is going to be 2. What is u of 2 is going to be 2 times 2 plus 1. This is going to be 3 times 2, which is going to give me 6, which is indeed u2 that we have here, that's given. So again, this is true. So therefore P of n0 and P of n1 are true. So we have P of n0 and P of n1 are true, right? So, and we saw how we check it. So basically you pick n0, which the index that we have here, you replace in the relation that we are trying to prove, because this is what we are trying to prove. So you cannot replace it here, not on this one, right? So you replace it on what we asked you to prove. So this is what we are asked to prove. So when you replace u1, you replace n by 1, you get this expression, because the induction is on n. That's why I put Pn over there. So, and again, you replace on the u2, you get again, and the expression that we are trying to prove, you get 6. So that's the base case for that one. Now for the inductive step, this is the inductive step. So what we do, we assume that P of n0 and P of n1 and P of n2 and up to P of m are true. Then the goal is you must show that P of m plus 1 is true. So we assume all this to be true, right? And we want to show this is true. So this is what we mean. So we assume these are true, and the goal is to show that this is true. Now what I'm going to do is, because all these statements are true, I can focalize on the last one, because all the statements behind are true because m is greater than everything behind that. So that's going to work. So because P of m is true, this implies that u m equal to m times m plus 1. That's the P of n is true, imply that the expression is true. So we must show that P of m plus 1 is true. That said, we must, there's S here, you must show that that u m plus 1 equal to m plus 1 times m plus 2. Why we get this? Why is m plus 2? Because this was um, that was expression that is assumed to be true, and I replace m by m plus 1 everywhere. So this was m plus 1 plus 1, it give me 2. So we need to show this. So what we are going to do, we are going to go from this from this statement. So what is u of, we give we was given that um equal to u n minus 1 plus 2n. So that means m plus 1, because I'm trying to compute to go from this side then to get this. So this m plus 1 is going to be, I just replace in this formula. Basically this is going to be this is m plus 1 minus 1, because we replace m by m plus 1, then plus 2, then this is m plus 1. So this is going to be m plus 2 m plus 1, right? So but what happened is in the inductive in the inductive step, we assume that was equal to this. So this is assumed to be true. So we replace, so this is this is going to be m times m plus 1, right? Then plus 2 times m plus 1. So this replacement is because of the inductive step, right? Or inductive hypothesis. Just because that statement by himself saying that p of k is to p of m is true is the inductive hypothesis. So inductive hypothesis, I can call it inductive hypothesis or inductive step, inductive hypothesis. So this what I have a common factor here, so it's going to be m plus 1, then inside I have m plus 2, and this is indeed what we was trying to prove here, this expression, right? So we conclude our proof. So that was how to prove using a strong induction. So I'm going to pick another case where we have to deal with the Fibonacci sequence. Before we even start the Fibonacci sequence, I'm going to give you some brief review of the Fibonacci sequence. So so the Fibonacci sequence, we usually not represent it this way. This is fn n equal to 1 up to infinity, right? So we define by f0 equal to 0, f1 equal to 1. Then we give this recurrent relation fn plus 1 equal to fn plus fn minus 1, right? So this expression by itself, you can write it differently. So if, let's say I want to get fn plus 2, f2 for example, fn plus 2, what I'm going to do, I'm just going to replace n by n plus 2 in this actual relationship. So if I want to get fn plus 2, this is going to be, what I do is just replace n by n plus 1, because if I have fn plus 1, right, then plus 1, this is indeed fn plus 1 plus fn, because I replace n by n plus 1. So this is n plus 1 minus 1. This gives me, this imply you have fn plus 2 equal to fn plus 1 plus fn. So this another relation that is again for the Fibonacci sequence that I derive from this, and you can repeat that process. You can derive many representation from that actual expression. So it's very important to know this, and also the base case is f0 and f1, which are 0 and 1 respectively. So you have to know that also. And from this, what you can see is that if I want to have f of 2, f2 is going to be f2 is going to be f0 here. So f2 is going to be f0 plus f1 basically, because I replace this by 0, I get f2, so it's going to be 0, this is going to be 0, so this gives you us f1 plus f0, so basically f2 is going to be 1 also. Now let us use that technique to prove something. So we have for all n greater than 0, the summation of k equal to 1 up to n of fk square equal to fn then fn plus 1, right? So we are trying to prove that using strong induction. So for the base case, because we have f0 and f1, so I'm going to be let's call this my property, this is my p, and again I'm going to use strong induction. So for p of n0 is what? So n0 is the base case, n0 is 1, no, it's 0. So I'm going to replace in the relationship. So the summation of k, we cannot get 0, we have to start at 1, so n1, so we cannot get from n0, so n1 is what? Because it's strictly greater, so it's going to be 1. We are going to start at 1 because this is strictly greater than 0, so this is going to be the summation of 1 from 1 to 1 of k square. This is going to be f1 square, and f1 is 0, is 1, so it's going to be 1 square, which is 1 because of what we have here. So this is f1, right? That's the definition of Fibonacci sequence. So f1 is given. Now if you compute, if you want to compute proof of n2, is going to be n2 equal to 2. So what you're going to do is you're going to do the summation of k equal to 1 up to 2 of fk square, which is going to be f1 square plus f2 square, right? Now we saw from here that fn plus 2 is this. So if I want to get f2, I just replace n by 0, so it's going to be f1 plus f0. f1 is 1, then f0 is 1, so f2 is going to give us 2. F2 is going to give us 1, right? Because this is the f2 is going to be f1 plus f0. So f1 is 1, then f0 is 0, so it's going to give us 1. Then we can see that this is what is f1? f1 is 1, so okay, so this is 1 plus 1 square, this is going to be 2, right? But if I replace again in my expression here, so if I replace on the other side, I'm going to get so I'm going to get f1 times f2, so it's going to be what is f1? It's going to be 1 times f2 times 2 is going to give me 2, right? So you can see that on both sides, so f1 times if n is 1 times f3, okay, so this is going to be, if I want to check for 2, it's going to be 2 plus 1 is going to be 3, so this is going to be f3. So what is f3? If you go back here, f2 is this f3 is going to be f2 plus f1, so f2 is going to be, so f2 is going to be 1, and then f1 is 1, so you're going to get f3 is going to be 1 plus 1 is 2, then it gives you this 2, right? So that's how you proceed. So basically we check for these base cases and that indeed works, right? So what we do is we assume p of n1 and p of n2 up to p of m are all true, right? So these are true respectively, they are all true. This implies we want to prove that p of n m plus 1 is true. So we want to prove that. Now we went up to this level. Went up to this level. This was the base case basically. So this was the base case, and for this step we assume this to be true. We want to prove this is true, right? So I'm going to assume that if I have p m is true, right? Is true by the inductive hypothesis. That means that said we are saying that the summation of k equal to 1 up to m, right, of m to m of fk square equal to f m times f m plus 1. So because that's the inductive hypothesis, we must show that in the inductive step we must show that p m plus 1 is true. That said, show that the summation of k equal to 1 up to m plus 1 of f k square equal to f of m plus 1 then f of m plus 2, because I replace m by m plus 1, right, in this expression. Now that's what we have to show. So I'm going to consider the right side, the left side, and try to get the right side. So if you have the summation of k equal to 1 up to m plus 1 of f k square, so this give me what? This is equal to f1 of square plus f2 square plus f m square plus f m plus 1 square, right? Because before we get fm, you see fm plus 1. So this summation, so this is the summation of k equal to 1 up to m of fk square. So this is the of k square, then plus f m plus 1 square, right? But this summation based on our inductive hypothesis, which was this, we assume that to be that expression, right? So we can replace that by fm plus 1, because we assume that to be true in the inductive hypothesis. This is fm, then fm plus 1, right? Then plus fm plus 1 square. So we can pull out fm plus 1 out, so it's going to be fm plus 1 out, then you have fm plus fm plus 1, right? We have that. But look at this expression again. What we have here, we found that fm plus 1, then we have fm plus 2, fn plus 2 equal to fn plus 1, plus fn. So you can see that this expression is the same as what we have here. So this is fn plus 1, and this is the same thing, fn plus 1 equal to fn plus 2. So you're just going to replace this by, so this is going to give you fm plus 1, then fm plus 2, and this conclude our proof. That's what we was looking for. So that's the technique on how to use mathematical induction, strong induction, to prove something. And the main difference is when you try to do the base case, and also when you are dealing with the inductive hypothesis. Okay, so this last minute I'm going to use it to give you some hints about what you have for the homework. So there's something that you have to consider on your homework. You have this summation of k equal to 1 up to n of 2k plus 1 over k square k plus 1 square. This is the same as the summation of k equal to 1 up to n of 1 over k square minus 1 over k plus 1 square. The reason why we need this transformation is that when you expand this expression, when you expand this, because you are trying to write this without summation. If you expand this, the expand mean what? That means you are going to, if you start by 1, you are going to have 1 over 1 square minus 1 over 1 plus 1 square, right? That's the first term. Then you say plus, you have 1 over 2 square, and then plus minus 1 over 3 square, right? So this is 2, and you're going to keep going that way. This is 2, right? So what you observe is that this term is going to cancel with this, and that the repetition, some terms are going just to cancel like that. So because if you go to the next step, you're going to have plus, you're going to have 1 over 3 square plus minus 1 over 4 square, right? So again, this is going to cancel with this. So I'm not going to go further. So this for you to figure out. So you're going to cancel some term, and then you're going to get something that's a little bit nicer, and then you prove that expression. So that's it. I'm not going to give you more hints about that. And the second one is about this summation. We give you Rn minus Bn equal to A minus B, the summation of k equal to 0 up to n minus 1, A n minus 1 minus k, then b k. You are given that summation. So the question is, we are asking you to prove that, right? So to prove that, you're going to, again, it depends on what technique you really want to use it, but mathematical induction is strongly recommended to use to prove that. So how you proceed to on proving something like that? It's not so difficult, but you must observe something on that expression. So what you can do is, using mathematical induction, you are going to show that that expression is true at the base case, then show that it's also true at the n plus 1. So the base case, you have to prove it at n plus 1 is basically a n plus 1 minus b n plus 1 equal to a minus b, the summation of k equal to 0 up to to n plus 1 minus 1, and then a n plus 1 minus 1 minus k, then b k, right? So that's what we have. So basically what I suggest is you can simplify this further. So this will give you just n, and here's going to give you n minus k, right? I think that's the case. So you're going to get something like that, and try to work, maybe you can try to work this side out, then see if you can get something like this. But it's for you to decide how to proceed. But I just gave you some hints. You can expand this expression, you can expand this, then multiply this with that block and see what you get. If there's something that you can use it, and also know that this is true. So if somewhere you have this summation, you can replace it by this what you have here. So that's all for what I have today, and probably Friday or next week I will post another video on again, probably recursively define something, and also structural induction. Thank you.